Today we're going to start algorithmic accountability. That is to say, an analysis of how algorithms have an effect in society. I originally had a statistics lecture scheduled. I decided to postpone that a little bit because next week your final project proposals are due. And so I wanted to talk about some of the things that you may be interested in including in your final projects. This is part 1 of 2 of algorithmic accountability. We're going to spend 2 weeks on this. The centerpiece of today's class is going to be a deep unpacking of a famous piece of algorithmic accountability journalism, possibly the most famous piece, which is ProPublica's machine bias, where they analyzed the Compass recidivism prediction algorithm. So this is an algorithm used to decide who gets bail. This is a pre-trial risk scoring algorithm, right? So this is literally an algorithm where individuals' freedom hangs in the balance. Of course, it's natural that it should come under a lot of scrutiny, and we're going to talk about the analysis they did and what they concluded, and honestly the can of worms that opened up, because it was the beginning of some very complicated questions. First, I want to talk about some previous work in algorithmic accountability, some other things that have been done, and even before that, the first thing we have to do is, I guess, scope this. And the way I'd like to do that is to list out all of the places where algorithms have an important effect in society. So let's do that. So where are algorithms used in society in consequential ways? So obviously, algorithms are used in society for all kinds of stuff, right? You know, music recommendations and checkout machines and so forth. But they're also used to make decisions that can be quite consequential. So, yeah.
Real estate.
Real estate. Tell me about that.
So deciding whether someone is approved for a mortgage or approved for a lease, or even where to invest in housing, and what kind of people to market that housing to.
Okay. Yep, so classic stuff tied into, any of you know the phrase redlining? Yeah. Okay, so that was the policy of steering minority homebuyers away from certain neighborhoods, which is, of course, illegal, became illegal in the 1960s, but still kind of happens in certain ways, and we'll look at analyses of that. Okay, what else? Credit scores, yep. That's a big one. So that's also related to lending. I will actually look in much more detail at the effects of algorithmic default prediction on lending in the next class. It's going to be another exercise we do. Hiring? Yep.
Oh yeah, Amazon was just in the news for their hiring. They use AI for their hiring, but it was found to have a bias for male candidates. They stopped.
Yeah. Yeah. Well, So we're gonna look at this question of fairness in great detail. That's kind of what we're doing here. Okay. What else? Welfare distribution. What kind of algorithms would we have in welfare distribution?
Just who is eligible.
Okay.
And maybe what quantities they receive.
Okay. Do you know of algorithms or models being used for that?
I think like the high profile ones are like the ones in Virginia Eubanks' book.
Yeah, right. Yep. Yeah, so that book's going to come up. A bunch of this work is going to come up Okay, what else?
Like medicine, somehow like healthcare application.
Yep. There's all kinds of places in healthcare. So diagnostic models, that's a big one, right? Or prognosis, who gets this very expensive procedure? It's nice to imagine that anybody who could possibly benefit from a medical procedure gets that procedure, but that's not how healthcare works, right? You have even if it's a large number, you have a finite amount of resources, and so you have to make allocation decisions, which means that some people aren't going to get a very expensive test which has a very low probability of finding a problem. So you have to make these decisions. Medical ethics, it's a fascinating field. What else? Insurance, yeah. Insurance of all types. Interestingly, insurance is probably the first method where algorithmic techniques were used. And we're going to talk about what I mean by algorithmic techniques, right? That's, we can also just say statistical models or actuarial models, which is how insurance rates are calculated. Large parts of probability and statistics were invented to make insurance work out.
Policing? Policing?
Policing, yep. So I'm going to start over here. How can algorithmic or statistical methods be used in policing?
Computer vision, for example, for identifying criminals.
Yep, okay, so face recognition. You said predictive policing. So where are crimes going to be committed, or who is going to commit them?
Placement of cops.
Yeah, that's normally part of predictive policing. And in general, we can add this category of criminal justice. So risk scores, who's likely to be rearrested or commit a crime. And that can be pre-trial or post-trial sentencing. There's a bunch of different places where predictive models. So you have, should we release this person on bail? That's pre-trial. What sentence should they get? Should they get released on parole? Stuff like this. What else? There's at least one remaining huge category. Yep, that's a good one. All right, so student testing, teacher evaluation, hiring and firing within education, all kinds of places.
Advertisements and business promotion.
There we go, yep. Advertising and marketing. So optimization of ad purchases, micro-targeting. And as long as we're going to talk about micro-targeting, let's talk about politics. So trying to persuade voters, sending different messages to different people, that's micro-targeting or personalized advertising. Predictive models, like election prediction. Now, for you and I, election prediction is sort of a journalism function, right? Like we're going to inform people who's leading in the polls, ultimately. If you look at it from the point of view of a campaign, election prediction changes the strategy that candidates use. They changed where they campaign, where money is spent, what issues and positions they take, because of course they will try to take the issues that will get them the support they need to win. So those predictive models can indirectly have influence on the policy positions of our leaders. Kind of crazy, huh? There's still a big area that we don't have on this list here. What's that?
Social networks.
Social networks. Yeah, that's a good one, isn't it? So we've been talking about this in your filter design assignment. That's a big field. We'll sort of leave it at that for the moment. I want to add at least one more. Finance. Algorithmic trading. Models for investment. This is a heavily algorithmic field, possibly more so than any of these others. Right? I mean, when we say a quant, right? You all know that phrase. We're talking about that word came from finance. The allocation of money in society is heavily dependent on statistical models and algorithmic methods. Yeah.
So I feel like a lot of these, maybe others disagree, but a lot of these are places where we expect or we already know that they're sort of controlled by algorithms, or that algorithms are heavily employed in all these things. But what are the categories where the general public or even people who are more specialized like us are not paying attention? Like everyone talks about algorithmic accountability and policing and credit scores and that sort of thing, but like where are we not paying attention to in your estimation?
Well,
like everyone's talking about algorithms and social networks, or politics. But
yeah, so hey, let's circle the popular ones. How about that? And then we can see, okay, so everyone's talking about policing right now. We're going to talk about it too. And criminal justice, social networks, politics. Yeah, there's a fair amount of talk about that. So hey, that leaves everything else. Credit scores, people talk about that.
like where does there need to be reporting, I guess is my question.
Okay.
And which of these categories also, the ones that are popular and which have most impact on people's material lives?
So I would say finance. That's my answer. I think there is a catastrophic lack of accountability for the use of statistical methods in investment decisions. And it's not, in some sense, it's not really a problem with the use of statistical methods. It's the problem of deciding what to invest in using only the metric of how much money will it make me, right? This is not a new problem. We just have a new form of this problem.
A lot of these categories are also things that you could submit a FOIA or a FOIL for, like police, criminal justice, politics, whereas healthcare, sure, education, but some of the more important ones are masked by private industry. So
Yep.
how do you get access to those to help you?
Are there people that are building models, like to reverse engineer the models that are being used in finance? If that makes any sense?
Sort of, yeah. We'll talk about finance a bunch more, in part because I think it's really fascinating and important. Oh, another thing under policing is DNA testing. I was talking to someone last week who is on this. She got a magic grant to compare the outputs of various DNA matching algorithms from different vendors. And she's having the same problem that you just mentioned, which is that these algorithms are trade secret, right? The companies that build them don't publish them, and yet they send people to jail. Here, so I'm going to circle finance as something we can talk about more. And we'll talk about it a little later today when we discuss the final projects. I went through that deck really briefly last class, but I'd like to actually have a discussion about it today. Okay, so lots and lots of places where algorithms have influential effects. This was a list that I made up earlier. Let's see how it pairs. Oh, price discrimination and terrorism. Yeah. So that, and search. Wow. Yeah, so this is a big list, and you can add more things to it. Price discrimination is the practice of charging different people different amounts of money. We'll see examples where that is happening. That can very often turn into class discrimination. Generally, people who have less money have poorer negotiating power, which means, ironically, you can charge them more. Terrorism prediction. This was it sort of exploded into public consciousness after September 11. There was briefly something that was supposed to be called the Total Information Awareness Program, which was very sort of Big Brother-ish. Most of the things that they wanted to do have since been taken up by the DHS and the intelligence community. We're going to look at algorithms for trying to, like machine learning algorithms to guess who's a terrorist, that type of thing. Scanners at airports, who gets stopped and searched. And this is a uniquely challenging domain, both because it intersects basic civil liberties and freedoms and because the number of people who are actually a threat is so small that anything you do is going to be swamped by false positives. So this is a basic challenge in actually several of these fields. Okay, so algorithms are everywhere. Again, just sort of as a framing exercise, there's a big discussion happening in Silicon Valley right now, which was barely happening 2 years ago. It's really the election kickstarted all of this. And a lot of people are interested in sort of technology ethics. This is one framing for the ethics of technology. The framing is the unintended harms in technology, and they've sort of split into a bunch of zones. And so we're going to talk mostly about this, machine ethics and algorithmic biases. This is huge right now. Disinformation. We're going to have a class on disinformation. I think it's called Truth and Trust, the class we're going to do. It's one of the last few classes. I am also extremely interested in this, economic inequalities. I suspect that is going to have far more impact on more people's lives than just about anything else that we have on the board, including things like criminal justice. I feel like it's very understudied. And I think part of the reason it's understudied is it's very hard to get a handle on because it's so systemic. You can think of it as algorithmic critique of capitalism, which is just getting off the ground. But anyway, mostly we're going to be here today and in the next class.
Zone 2, the addiction dopamine competition.
Oh, this is the idea that we're designing Facebook to make you,
Platforms.
yeah.
Oh, okay.
Yeah, we're building products that are designed to be addictive, right, which is not healthy. This is a site which is specifically about algorithmic accountability, algorithmtips.org. And what this is it's this list they generated of algorithms used in government. And so, for example, so here's a few, right? Let's see, what should we search for? What type of algorithm should we find?
Child welfare?
Okay, so here you go. Method for calculating number of children directly certified for free school meals and other social benefits.
Wait, why would there be a method? Don't they just have that number? Why, they have to estimate that? Gonna drive me up.
Yeah, I mean, I don't want to speculate, but we could find out. I don't want to do it right now. Let's just try welfare as opposed to child. Oh, that's the only one. What if we just do child?
New school test
Knock and talk situation?
Huh. Interesting.
It's knock and talk. That sounds like a terrible idea.
Wait,
It looks like it's a evidence collection
Yeah.
system. Okay.
Oh, like knock and talk.
Yeah,
Yeah,
right.
yeah,
Knock
yeah.
on the door and talk to them. Yeah.
Except it's just.
I don't know.
This is a scoring system for evaluating schools. Anyway, so this just goes on and on. And many of these things are not algorithms per se. In fact, many of them probably don't even have code, right? They're just methods. But although we're now talking about algorithmic accountability, it's not like statistical models are new in government. They've been used for at least 100 years. Any sort of scoring system, any sort of predictive model, they've been used for a long time in a lot of fields. It's just they're becoming more sophisticated and more consequential.
What is even the line between an algorithm and a statistical model?
I don't know.
Okay.
What's the line between statistics and machine learning or machine learning and AI? Right, it's not really important. The important characteristics here is that there's some, let's say, mechanical method for coming to a decision, and we want to evaluate that method. So that's algorithm tips. How they got it is pretty fascinating. They wrote a paper about this, which is linked from the syllabus. And they, basically, these are all the search terms they used. And you can see some of them are bold. I think those are the ones that they came up with themselves, and then they used analysis of related phrases. So what else appears in these documents to find the non-bold ones. So there's a lot of different names for these types of techniques. Algorithm tips is cool. There is a major limitation with algorithm tips, which is that it's only government. And you can see which government departments they pull it from. Interestingly, Health and Human Services has the highest number. I find that fascinating because it's I suppose, the most human, right? It's the Department of Energy must have all kinds of formulas for figuring out how much electrical wiring is needed for a state, but that's not really, that doesn't appear in the search results, I guess. This is about the extent of public knowledge of the FICO score. The FICO score is the standard credit scoring algorithm. That is to say, we don't know very much. They don't release publicly where that score comes from. And most of the things on this list that we just came up with, there's very little public information about how this stuff works. So we had the question earlier, how do we investigate these algorithms? And this is something we'll come back to a number of times, but any initial ideas, strategies for investigating non-public algorithms?
Encourage leakers.
Encourage leakers, sure. So inside sources, yeah.
Did you guys say FOIA request?
You can't FOIA a company.
Oh, private, sorry.
Yeah, that's the issue.
I mean, try and build the model yourself and see if you can get the same results. So.
Yep. So you can try to replicate the results, assuming you can get the results. So that's a big deal, right? can you get the output of the algorithm? Sometimes you can. That's kind of what ProPublica did with the Compass algorithm. It was a model to predict whether people would be rearrested within 2 years. So they just waited until everybody was rearrested, or waited until 2 years went and saw how many of those people were rearrested, right? So you get the ground truth. Because arrest records are public.
Talk to people who've been affected by the algorithm.
Mm-hmm.
What
Yep.
Like a qualitative critique of the algorithm?
Like especially like who bear the brunt of the decision.
Yeah.
They must have a lot
Yeah.
to say like how this impacted.
Yeah, I mean, definitely you should talk to the people who are affected by the algorithm. The challenge there is that even a very good algorithm is going to have some very bad results because there will be errors. So how do you do balanced reporting? Because you can always find the case where something bad happened. So okay, if that's true, then how do you decide whether a particular algorithm is good or bad? What does that even mean?
Yeah. Also, the odds are horribly stacked in favor of private industry, because if you're looking at like trying to reverse engineer an algorithm that a team of the best engineers have been working on for with all of the resources and with uninhibited time versus a newsroom.
Yeah.
Very few newsrooms are equipped to do that, and I think that's why ProPublica was able to do such a, one of the reasons they were able to do such a rigorous analysis is because they have the resources and the talents. So.
Yeah, although, as we'll see, I don't think it was that resource intensive actually. It mostly involved
Well, maybe not
waiting.
that resource intensive, but they have really great people working there.
Yeah.
Like really, really smart, talented people.
Smart, talented, well-trained people like all of you. Go forth. Yeah, so there's issues. Other strategies for investigating private algorithms include, so if you can run the algorithm, then you can test it, right? So you can, if you want to get into a situation where you can feed inputs into it and see what happens. And for example, you can do this with Facebook. You can make fake profiles, you can try posting different things. We're going to look at, a little bit later today, an experimental method for analyzing how the newsfeed algorithm works, which is very clever. It's very, very simple and very easy to do and very clever. Organizations like the Wall Street Journal have done things like their red feed, blue feed piece, which just created 2 different profiles and set up different friend groups just to understand how you could end up in different information worlds. There's a lot you can do just by interacting with the algorithm. So while these algorithms are often trade secret, there are actually methods for investigating them. And if it is an algorithm of significant public interest, you can also make the argument that it should be public, right? You can do a story. So this is like kind of like doing a story that says, why isn't this data publicly available? You can sometimes, when you can't get the data, you sometimes still get a story, which is, I can't get the data. So you can do a story which is like, you know, we've talked to 10 people whose lives were badly affected by this algorithm. Why can't we see it? You can do that story as well. You can apply pressure for transparency. So for the next part of our discussion, I want to go through just a bunch of previous algorithmic accountability work and just sort of a brief survey of what's been done. This wasn't a piece of journalism. This was actually a blog post, but this was an analysis showing that New York City's teacher evaluation scores weren't doing what they were supposed to do. And let's get the original thing so we can look at it. And I will try to unpack this a little bit. I know that chart doesn't make a lot of sense on its own. So this is going back a few years now. And what we are looking at is a thing called a value-added score. So the idea is you look at the test scores of the students. But you don't want to look at just the raw test scores because the student population is going to be different at different schools. The students come in with different levels of skills already. So instead you look at this measurement, which is how much have they improved? And this is the idea behind the value-added test scores. And the issue that he's pointing out here is that we really have no way to figure out what it means. But this analysis suggests that it doesn't mean all that much. So here's what's going on here. The horizontal axis is the teacher's value-added score for, and these are released publicly, for a particular subject for 1 year, let's say 4th grade math. And the y-axis is their score for the same subject for the next year. So let's say 5th grade math, or it could be 6th and 7th grade English or something like that. Now, you would expect that if this is actually measuring teacher quality, that the teacher's quality of teaching is going to be similar between 4th and 5th grade math, right? The idea here is that you're measuring some underlying latent teacher quality variable. The issue is that we get only a very weak correlation, right? So we would expect that this was more or less a linear cluster, right? It should be a lot flatter. And the fact that it's all over the map means there's no correlation here, which means that you either have to assume that in general there's no relationship between how well you teach one grade and the next grade, or the metric isn't working. So that was the argument in this analysis.
How do you get 0 and 95? Like some of this just would make me wonder if I saw those data points.
Yeah, I don't know. We'd have to dig into exactly how this scoring system works. So I like this example for a variety of reasons, one of which is it's a very clever way to test the output of this model without actually having access to the model, right? We don't have to know how this is being calculated to know that it has not captured the thing which it was designed to capture, right? So we look at only the output, not even the input, and we can tell it's wrong. Here's one of my favorites. This is an old piece by the journal. And what you're looking at is the relative price of a standardized basket of goods, right? So how much for a ream of paper, an SD card, and a stapler at buying online, right? So this was Staples, which is an office supply retailer. And what they did is they effectively accessed their website from computers in every zip code. So they used a commercial proxy service to route the requests through each of these places. And looked at how often they got higher prices than the baseline. So what pattern do you see here? Cities have lower prices, right. Why do cities have lower prices, right? So now we're going to ask, what is the company doing?
Oh, that's great. I thought it was light.
Proximity to their warehouses, their supply, like how much it's going to cost them. They're basically, well, I don't know, my hypothesis is that they're shifting the burden of shipping the product to rural areas onto the rural consumer.
Mm-hmm. Yeah, so that's a reasonable explanation. And I think shifting the burden is the right language. Not everybody does that. In fact, in public systems, we always end up spending more on rural areas. So, for example, and this is a famous case of price discrimination used by economists. In England, for a long time there were laws saying that you can't charge people more to ride the train to faraway stations, right? It's got to be the same cost per mile no matter how far out you're going. But of course in the rural areas and the smaller lines there's fewer riders, so it's actually per capita more expensive to support them. The New York subway system is similar, right? It's the same cost whether you're riding from Far Rockaway or 3 stops. Highways, basically all transport systems subsidize the lower population areas, but private companies do not. So that's one theory of what they're doing, is basically they're just passing the cost of shipping. Although it's not clear to me if DHL or whoever they're using is actually going to cost more to go to rural areas. Normally, if you look at the shipping rates, it's sort of like they divide the country into 3 or 4 regions and everything within that region is the same cost. So it's not clear to me that this is reflecting their shipping cost. What else could it be?
Competition.
Competition, say more? Say more about that?
Oh, well, I think you're going to have more competition and more competitors in large cities
Mm.
than rural areas. And so you're going to have to adjust your price to compete.
Yeah, so clearly on some level they're charging this price because they can. If nobody was buying at that price, the prices would shift. But there's an interesting question here, which is, how are these prices actually being set? Is there some operations executive who's sitting there with a spreadsheet every week and setting the prices? Is that what's happening? Yeah, I suspect that these prices are set algorithmically. And I think actually, and this would make a great final project, that you could actually get this result with an extremely simple little algorithm, which is basically just put an optimization algorithm on total sales, right? So you're all familiar with optimization. Let's say a one variable optimization problem where you have some function that you're trying to find the maximum of, right? So in this case, it's sales, and this is price. So you try to find the price at which the sales are maximized. And there's many algorithms for doing this. So one of the simplest is hill climbing. You change the price. Let's say you add 1% to it, and you see if the total sales go up. If they go up, you keep adding 1%. Is that closed?
Yeah.
And if it goes down, then you subtract 1% of the price, right? So all you're doing is you're just chasing the local gradient, and at any given point, you compute the gradient. I guess in this case, just the derivative, right? Because it's a one variable problem. By numerically, right? So you just evaluate the function at 2 different points corresponding to 2 different prices. That tells you which way is up. You chase it until you get to the top. So which you can do in 2 or 3 lines of Python. So I suspect that this pattern that we see is generated by extremely simple pricing scripts. And what we get is that rural areas are charged higher prices. And because there is a correlation between urbanization and wealth, what you get is poorer people have to pay more. So probably the engineer who set up this price optimization algorithm had no idea that that would be the effect. And so this is potentially one of the issues with the automation of these types of things, is that you can get bad effects and not even be aware of it, right? It's not that charging poor people more money for the same thing is new. That is a standard effect of capitalism. The problem now is that you can do it without thinking or knowing about it, potentially. This is one we looked at before. This is reverse engineering of political micro-targeting through email. This was a ProPublica piece from the previous election. And oh, there you go. Look, I've just got the headline. Amazon scrapped an AI system that discriminated against women. There you go. In the news today. We've broken this one apart. It's TF-IDF clustering to combine the variants of the email. Interestingly, the way they did this was they crowdsourced the data collection. So that is another strategy for trying to do algorithmic accountability. Here's another big piece they did. Insurance premiums were historically higher in minority neighborhoods. We've had for decades now laws saying you can't do that. But it still seems to be the case that they are higher in minority neighborhoods, even accounting for risk, right? So you have to account for risk because not all neighborhoods and not all drivers have the same risk. The risk by zip code is available. So that's public record. So that's what this x-axis here is. So average payout per car per year. So in this case, that would mean basically each driver claims an average of $200 a year. What actually happens, of course, is that most drivers claim nothing, and then some get into accidents. So what they're doing here is they're fitting these smooth curves to the patterns in the different neighborhoods. And I mean, I don't know. There's a lot of variance here, right? You can see that these curves don't actually track the data that closely, but you can also see that generally it's higher in minority neighborhoods for the same level of risk.
I don't super understand this chart. Could we unpack it?
Okay, the vertical axis is the.
Where are the zip? I don't see where the zip code.
Okay, each dot is a zip code.
Oh, okay.
Yeah. So each dot is a zip code.
Average.
Yeah, exactly. So the y-axis is the cost of insurance in that zip code for a particular insurer, and the x-axis is the payout in that zip code for averaged across all insurers.
I guess it seems like a lot of zip codes. It seems like more zip codes than I would imagine in one.
Well,
Although I don't know a whole lot about Chicago or Illinois, I guess.
I think the zip codes are based on population, right? So there's a lot of zip codes within a county,
Okay.
within a city, et cetera.
Yeah, those were not just zip codes in Chicago. Those were zip codes.
no,
in
it's Illinois. Yeah, exactly. Yeah.
Okay, but this subheader says Chicago area disparities. So the other graph I was looking at thinking this is just Chicago?
No, it's all of Illinois, and they actually do it for several states.
Okay.
I think it was four states.
This is an analysis of, this chart is a little hard to read as well. So what this is, it's the correlation between the change in price. So this is an analysis of surge pricing. You're all familiar with surge pricing? You know what I mean by that? Anyone not familiar with surge pricing? Okay, so an analysis of surge pricing. The change in the surge price versus the change in the number of cars nearby. So what they're looking at is, do the surge price changes actually lead to more cars? And a positive correlation coefficient, so everything above here, is yes. So you can see that after 5 minutes or so, there tends to be more cars. But the effect is different in different neighborhoods. And again, the sort of variable of interest that they were looking at here is the racial composition of those neighborhoods.
So we took 5 different streets and
Neighborhoods in DC, yeah.
Yeah, like we're not in DC, so these don't mean a whole lot, but this basically means that Paulding Street, Navy Yard, even when there's surge pricing, more cars don't come.
Right. Yeah, or slower.
Yeah, so it just
Yeah.
makes it more expensive for that neighborhood without actually providing the thing that surge pricing is supposed to do.
Right. So you don't actually get better service, right?
How do they connect this?
By using the Uber API.
Oh.
So the API will tell you both the current price or what the surge pricing factor is, right? Because it goes to like 1.5 or 2 or something. And also the number of cars in a neighborhood.
Oh, you have access to that?
Yeah.
I didn't know that. Oh.
I don't know if you still have access to it, but so here's a technique as well, is use the API. Analyze what you can get from the API. Now, they said in their article, we don't think that Uber is trying to do worse in neighborhoods with more minority passengers, right? Like, and this is a key concept in reporting on discrimination is don't get fixated on intent, right? You don't have to find somebody who really wants to be an asshole or really, some really racist marketing exec to have a story. Unintentional disparities also matter.
Yeah, and I'm just thinking in terms of this, isn't surge pricing also based on the number of people looking for a ride in relation to how many cars are available?
Yeah, it's supposed to.
How many cars are available? And I imagine you don't have access to that, right?
Like how surge pricing, how they decide.
Well, I thought surge pricing was determined based on not only the number of cars available, but the number of people looking for a ride at that given time.
Yeah,
Yeah.
I guess what I'm saying is how do you know, since that algorithm isn't like
No, you're right.
public.
But is that something that they mentioned in the article?
No, so you're right that surge pricing is based on demand as well.
Yeah.
I don't think demand is available through the API, and I don't think it's in the article.
Exactly. That's.
Yeah.
But any one of these, so some of these are linked from the syllabus, but basically how these slides are set up is that if you take the thing at the bottom and you type it into a search engine, you'll get the story, because it's always the title at the bottom. So you can look at these charts content, and in fact, in this particular case, the code is available. So we could reverse engineer this whole story if you want to look at how it's done.
I have a really simple question.
Yeah.
If you were creating an app to use this Uber API,
Mm-hmm.
what would you write? And you're like, usually it requires like an app description. What do you say? We're trying to reverse engineer how your algorithm works to take you down.
Yeah, so, right, well, are they trying to take Uber down?
I mean, this isn't like saying that Uber is racist or that Uber is discriminating. It's more of like an indictment of like a systemic, a system that rewards companies and actors that behave in this way. So it's not like Uber is deciding to be particularly anything or the other. They're just trying to maximize profit like every other.
Yeah, I see, exactly. So I see this story as more of a comment on the issues with private provision of what has often been considered a public service, which is transportation, right? So as opposed to the subway, where there's a great deal of effort to try to reduce disparities in service quality and cost among different populations, right? So let's say close to the center and far out, which is also what we're seeing here. A private transportation company may not be trying to do any of that. And so it's an unintended and perhaps unexpected consequence of the shift from public to private service provision.
Where are you looking
You
create
say
an app
the
or something,
truth,
and it'll
okay.
say, it'll ask why was the purpose of your app.
Journal.
Do they care?
Yeah.
Do you think they really would just write random stuff to it?
Yeah, no, just write the truth. I mean,
That could put you in trouble, right?
I mean, you don't have to say I'm taking you down. I'm just
No,
like
of course.
curious. I'm like,
Like,
Well,
for
you
example,
can't, like, if
most-
you're-
most
but if
Reddit
you're
bots
doing
that
something
do,
for-
like actually violate Reddit's terms of service, and they just like have a term of service that is written very broadly that says like Reddit bots can't do so many things that Reddit bots are actually, just so that they can like remove your app.
Yeah, you can invalidate yourself.
yeah, so let's talk about this briefly because this is actually important. So first of all, the standard saying, or the standard approach in investigative journalism is go in through the front door first, right? So always ask, be upfront and honest about what you're trying to find out, why it's interesting, what you want to know, okay? So there's that. Scraping, there's been was a recent circuit court case that decided that scraping is not, or a violation of the terms of service of a website is not a criminal offense. Okay, so nobody's going to go to jail for scraping. Having said that, it can still be a civil offense, right? You can still get sued. So when in doubt, which is going to be most of the time for this type of stuff, talk to your in-house counsel for your news organization, right? If you're doing this freelance, then you need to talk to your assigning editor about this. Generally, what your lawyer will tell you is that if there's a clear public interest, then go for it. Because public interest is a defense in libel cases in this country, and actually many countries. But yeah, there are media law issues here for sure.
but that's basically like if the terms of service says you cannot prod and you only find out that it has like some sort of like public interest if you prod. So you have to prod.
Right, well, I mean, so you would have to be able to make the argument that that algorithm is important, and knowing how the algorithm operates can only be done using by testing. So there is actually a history of governments testing systems. So, for example, sending a similarly qualified black and white applicant into a bank to try to get a loan, right? And there have been, there's a long history of testing or enforcing anti-discrimination laws in this way. And so there is a strand of legal argument, which I don't know if it's ever been tested in court, but the argument is that, you know, we have a long history of sending people undercover to test for discrimination. So doing that by making API calls has got to be legal. So I would expect that you're in the clear, but this is why we have lawyers. It's to give us good advice on these questions. Okay. Let's go through this section, and then after the break, we'll do our analysis of machine bias. Race and gender bias are the most common topics for algorithmic accountability. Before we get deep into this, I just want to go back to this slide and say most of these things are not race and gender bias. Okay? So the algorithmic accountability community and research and stories so far has been focused on an important but actually quite narrow set of potential problems with algorithms. Nonetheless, that's what we're going to do today. Part of the reason we're so interested in race and gender bias is that there's a very clear legal framework around it. So this is one of the pieces of law around bias. In this case, it's looking at employment. But this was one of the first laws where this list, what is now known as a list of protected classes, appears, right? race, color, religion, sex, or national origin. So we have these categories. They are called protected classes, and it's illegal to discriminate on the basis of them in a variety of things. We're gonna look at that in much more detail tomorrow. No, we're going to look at it in much more detail right now. Okay, so these are some of the places in which it is illegal to discriminate on the basis of protected classes. So look at what we have here. Lending, education, employment, housing, and this public accommodation, that's things like the Americans with Disabilities Act, right? It says that you have to have wheelchair accessible entrances and so forth. Interestingly, and this is going to become extremely important when we talk about definitions of fairness, the public accommodation portion of this is the clearest example of the legal principle that different people are going to require different amounts of effort to be fair to, right? So the basis of the law isn't that everybody gets the same amount of effort or money or time or cost. The law is more complicated than that. It says some people are going to get more to make up for some disadvantage. So that is already built into the legal definitions of fairness. This becomes a very big discussion and is indeed the center of some very big arguments. This is a pretty broad list. There aren't many things that fall outside of this. This is most of the services that governments and provide.
About criminal justice, any of
That's true. That's true.
or the regulation of markets, finance,
Well, credit.
credit, but
Yeah.
credit extended, I guess, credit extended to individuals.
Yeah. Credit and housing, that's market regulation.
Yeah.
So these are some of the domains, and then I love this list. This is the protected classes, and you can see how they've expanded over time. So they're race, color, sex, religion, national origin. That's the Civil Rights Act. Interestingly, citizenship. This is relevant today with all of our debates over immigration. In most cases, you can't discriminate based on whether someone is a citizen or not. Obviously, there are some cases where you can, like voting. Age, pregnancy, things you might expect, but then veteran status, and more recently, genetic information. So I can't refuse to offer you insurance because of a genetic test, for example. So this is gradually expanding, and I guess we can expect that it will gradually get bigger. So you may think that if you're building an algorithm to decide on, let's say, credit scoring or hiring or who gets admitted to a school, for example, that it's very simple to not discriminate against race. You just don't give it the race of the person as input. This is where things get complicated. And this is what I want you to remember, is that race and gender correlate with just about everything. So let's look at that in a little more detail. I'm going to show you some data from this paper. This is a paper from, I think, 2015, where what they did is they built a model to try to predict protected classes, age, gender, political and religious views, things that aren't protected classes, relationship status as well, from a person's Facebook likes. So which pages had they liked? And let's just pause for a second and talk about how they did this. Because it actually has a lot in common with all of the recommendation systems that we've been studying. So they start with the user's Facebook likes. So the user-like matrix, right? This is very similar. This is basically a user item ranking matrix. And then singular value decomposition. So that's a matrix factorization technique. So they take each user and rather than having 55,000 likes for each user, they reduce it to just 100 components. You can think of these as the topics, right? So here we see component 1, component 2, and so forth. This is kind of like our user topic matrix or our document topic matrix. Doing this, you'll also get another matrix which tells you which topics are related to which pages. But in that case, we don't use that. What we're basically trying to do is dimensionality reduction on the users here. And then we do a regression model to try to make either a binary or continuous prediction for each of these variables, right? And so here we just fit the data. So we start with all of this user-like data, and we also have the values of these things we're trying to predict, and we fit a model, and we are taking a linear combination of the component scores. Any question on the method? Okay. Everybody get what we're doing here? This is almost the simplest model you can build. It could be slightly simpler if you omitted the singular value decomposition step, but then it would be kind of painful to do because you would need 55,000 coefficients in your regression equation. Okay. And the factorization also reduces noise. Interestingly, just like our topic modeling allowed the same word to mean different things in different contexts, the matrix factorization will do that for us here, right? So maybe liking BMW means one thing if you're a young man and one thing if you're an older woman, right? The matrix factorization will actually capture that. Okay, so when you do that, this is what you get. So these are the things you're trying to predict, and then this axis is how well you can predict it. This is an area under curve score. How many of you have seen AUC scores before? Knows what that is? Okay, so many of you know. All right, so this is useful stuff. This is the basic mechanics of classification, which is what we're going to do with the machine bias work. So this is important stuff. The idea is this. Let's say you're trying to predict whether they drink alcohol, right? That's one of the things they tried to predict here. So you build some classifier. In this case, it's going to be a logistic regression classifier. But it doesn't matter. It could be a decision tree. Could be anything. And basically, all of these classifiers, at some point, they're going to give you a numerical output, right? So we have some rule, and we say, prediction equals some function of the input variables, which I'm going to call x, right? X bar to indicate that it's a vector of all of these different input variables. And often it's something like a probability, right? So let's say in 0, 1. So if you do a logistic regression, you'll get something in 0, 1, which if you set it up right is a probability. So now you have to turn this into a yes-no guess, right? Because we're supposed to give a yes-no answer. Do they drink? Or maybe it's a multi-class problem, male or female, gay or not, whatever, over 50, under 50. Binary prediction problems are very common. so we need a threshold, right? So we're going to say, we're going to turn this into a binary prediction just by thresholding. So we're going to say f of x smaller than some threshold. Now, the threshold will control the trade-off between false negatives and false positives. So if I make that threshold really high, then I'm almost always going to say yes, which means I'll have many more false positives. If I make it 0, then I'm always going to say no. So I'll have many more false negatives. If you only want to get rid of false positives, always answer no. If you only want to get rid of false negatives, always answer yes. Okay? So the trick is not to reduce one of those to 0, because you can always do that. The trick is to balance them in an interesting way. So what we do is we write this graph, and we're going to say this is true positive versus true negatives. For historical reasons, because this first came up in radio systems, this is called an ROC curve. For receiver operating characteristic, which is the worst name, but anyway, that's what it's called. And, well, there's various ways to draw this, but I'm going to go with the Wikipedia way. This is false positive rate. This is false negative rate. And as you, so we know that we can get, oh, sorry, yeah. Thank you. False positive, true positive rate. So we know that we can get 0 false positives and 0 true positives by always guessing false. We know that we can get 100% true positives and 0 false positives by always guessing true. So those 2 points are always available to us. But then as we sweep the threshold, as we make the threshold, yes, we increase it from 0, we pick more and more positives, and we start sweeping this curve up. And as it gets nearer and nearer to 1, eventually we have 100% positives. So we get some curve that looks like this as we vary the threshold. And so these are the points, these are the trade-offs that are available to us. And normally, what we do is we compare that to the straight line between these 2 points. And the reason we do that is that that is the coin flip classifier. Okay? If we flip a standard coin that's weighted heads or tails 50-50, we get this point in the middle, right? Because it's going to get half true positives and half false positives. If we start weighting that coin and we say, well, let's weight it 70-30 through a negative, we get a point here, or we could get a point here by weighting it the other way. By setting, by just randomly guessing a certain percentage of trues and falses, we can get all the points on the green curve. So only this area of the graph, that tells us how good our classifier is. If we could guess perfectly, we would get just this one point here, right? We would have something that looked kind of like this. And if we ever built a classifier that had this type of performance, then we just guess the opposite and we'd have a better classifier. So the area under the curve is finally this whole area, right? We basically just take the integral as we sweep out our possible combinations of false positive rate and true positive rate, and it has to be over 0.5 because because 0.5 is what the baseline is here of guessing randomly. If we ever get something that's less than 0.5, we just guess the other way. So, going back to our Facebook analysis result here. So, guessing whether someone's parents are together at age 21, we get an area under curve of 0.6. That's just a little bit better than random guessing, so we get some information but not a lot. Whereas guessing gender, or well, you look at this, right? Hey, protected classes, race, sexual orientation, gender. We can guess with quite high accuracy, 0.93, which, so 0.93 means we have a curve which is, up like this, right? We get most of this graph under the curve. So this is the AUC is a useful way of measuring the performance of a classifier because it sort of integrates out the effect of setting a different threshold. It says, for whatever application you want, you can pick a false positive rate and a false negative rate that make you happy. We don't care what you're going to set that threshold at. This measures it independently. But anyway, 0.93 and 0.95 are very good predictions. So, there must be a bunch of pages that men like and women don't, and vice versa, because we can definitely figure it out just from your likes. And similarly with race. All right. Questions on that?
I had a question real quick.
Yeah.
For profiles that didn't fit one of the binary classes, did they just throw that away?
For profiles that didn't fit the binary classes? What do you
For
mean?
example, like Christianity versus Islam, if
Okay.
somebody was not one of those two, what did they do?
Right. What do they do with the Hindus and Jews? Yeah. I don't know. We'd have to read the paper to see how they coded it. Yeah. I mean, or a race other than white or black. Almost all of the racial stuff that you'll see is done with either white versus black or white versus non-white. There's very few that break out, actually, the different races. And then you have the problem of, well, what are the different races? And that's a mess. Anyway. So you can do this even with much less information. That analysis was done with 55,000 likes per person. That's a lot of information, although probably you only liked a few dozen. This is a simple an example done using predicting gender and political orientation from Twitter. This is just using different techniques, but you can see here the top row, they use only the data from what they had tweeted and their profile. And you can also use data in some cases to get better accuracy if you use data about who they follow. But you look at this and you see that you can get about 80% accuracy on gender and about 90% accuracy on politics just from Twitter data, right? So much simpler data set. And I would be very surprised if you can't get similarly high accuracy on race. So it's very hard to blind an algorithm to protected classes because, and of course this is the reason they're protected classes, is because they run so deep in society, they're correlated with just about everything else. So where you live, the amount of money you make, what your job is, your health history, all of this information will give you lots and lots of predictive power on protective classes, which means you can't really blind an algorithm to race. It can pretty much figure it out anyway. So that becomes a challenge to the entire idea of not using that type of information to make decisions. Oh yeah, here you go. Here's race from Twitter. Ta-da! So this uses different measures of accuracy, precision, and recalls.
What is Starbucks?
Whether they,
Like it?
yeah, I can't remember, but how did they get the data? Whether they followed it maybe? I don't remember now. But they did that because they wanted to look at also sort of commercial applications, right? So what can a company figure out about you? They use F-measure instead of AUC. F-measure is sort of a weighted average of precision and recall. We're going to get much deeper into all of these things, precision, recall, F-measures. Ultimately, all of these things derive from the confusion matrix. And yeah, we're going to do that after the break. We're going to talk about some machine bias concerns pretrial risk scores. And there's this lovely 538 piece that has an interactive simulation.
Wait, when did their graphics get so good?
When
oh,
did their-
it's a collaboration with Marshall Project?
Yeah, I think so.
That's why.
But here we go. Here's what a very Marshall Project story. But they've got this lovely little interactive here. So this is the idea. This is the sort of setting that we are in. We have a bunch of people. There's a classifier which classifies them here into 3 risk buckets. And then I think how this is set up is the high-risk people are always denied parole, the low-risk people are always awarded. And some number of the people who are granted parole will reoffend, which is these people here, and some number of people who are denied parole won't reoffend. So this is, let's call positive, you are classified as eligible for parole. So that would make this false positives, and that would make this false negatives. Okay? So sorry, this is post-trial. This is parole. This is not pre-trial. But a very similar system is used to decide who gets to be released on bail, or to advise judges on who gets released on bail. That's actually an important point, is that nobody uses these algorithms as the final decision. It's advice that is given to the decision makers who may or may not follow the advice. So that's the setting. And one of the parameters you have in controlling an algorithm like this is this threshold we were talking about. So if I crank this threshold way up, then a lot fewer people are denied parole, which is going to make the false positive rate how does this work? Here you go. The false negative rate is much higher, right? So I'm releasing fewer people. Whereas if I crank this way down, then I'm saying more people are high risk, which should reduce this rate. Why is this running the way backwards than I think it should be? Hang on. High risk people.
I think there's a delay.
It is catching up.
There we go. Okay,
Like,
here we go.
There's a bit of a lag.
Yeah, okay, so here we go. So we've got a lower false positive rate and a higher false negative rate, right? So there you can see directly we trade these things off. I actually think this is confusing, and there should be just one slider, which is the threshold for paroled versus not paroled. Because I think what happens here is randomly people in the medium risk category get awarded or denied, so it's a little bit confusing. Anyway.
And the categorization between the risk level is through, like, how do you decide what's low risk, medium risk, high risk?
Well, that's the exercise of picking a threshold. You have to decide, you can only pick a point on that curve. You have to decide which point you want. And that has to be based on how bad are false negatives versus how bad are false positives. So in this case, how bad is it to release someone who then reoffends versus keeping someone in jail who wouldn't have. Of course, you don't get to observe this if you're actually using the system. The people you keep in jail don't get to reoffend. But what you can do, and this is how these systems are built, is you calibrate it by making predictions on a set of data, all of whom are released. And then, rather than denied parole but wouldn't have reoffended, what you're looking at is we would have denied them parole if we were using this system. So in development, you actually get to see these 4 numbers, and in production, you don't get to see that number. So that's the setting we're in. And let's see here. The machine bias piece is a journalistic investigation into the Compass risk assessment tool. Compass makes risk assessment both pre-trial and post-trial. We're going to talk mostly about pre-trial. That means, do you get to be free on bail while waiting for your trial or not? They were able to obtain a copy of the actual questionnaire that produces the data. This thing has 137 questions. I've just shown you one here. It has things like, here, let's actually open this up and look at it. There's lots of fun stuff here. So this is up on Document Cloud. So you can see the things here. They've helpfully annotated it. So they're asking about things like, have you moved a lot? Or have you been suspended from school? How often do you feel bored? As well as, as they call it, criminal thinking. Yeah.
Hungry person has the right to
As well as things like the current charge and so forth. Notice that race is not on here. Now, of course, we know the race of the person we arrested, but the risk score does not use race or gender or age, right? No protected classes here. However, as we saw, you can probably make pretty good guesses as to the protected variables from this much data. So this is the input. There's 137 data points. And the core of, now of course there's a lot more that went into this study, but the core of the story is this table here, which I've reproduced from the methodology. And what we are looking at is the confusion matrix for everybody, for black defendants and for white defendants. So does everyone know what I mean by confusion matrix? Okay. So what the Compass algorithm actually produces is 2 things. One is a numerical score from 1 to 10, which you can think of as a probability of rearrest. Another is just based on thresholding those, a designation low, medium, or high risk. And I think how this works is, for public health analysis, the medium and high risks are merged into one category, high risk. And so these are the raw numbers. This is the confusion matrix, and then all this stuff, false positive rate, false negative rate, positive prediction value, which is also known as precision, negative prediction value, which is kind of like, positive prediction value is if of the people who we said would be rearrested, how many were. Negative prediction value is of the people who we said weren't, how many weren't. And so on. And then when you break it out for black and white, what you find is the false positive rate for black defendants is almost twice as high as the false positive rate for white defendants. Meaning that of the people who were predicted to be rearrested, 23% of those who were white in that group were not rearrested, whereas 44% of those who were black were not rearrested. Right, so the error rate is much higher. And this is the basis for the article. This is the basis for the claim that the algorithm is biased. So we're going to do this. We're going to step through this one thing at a time. Yeah.
Okay, so does the false positive rate mean that their parole was sentenced harsher because it was determined that they were more likely to recommit a crime?
So first of all, this is pre-trial. So there's no parole here. This is were they released on bail or not.
Oh, released on bail. Okay.
Right? So that's important from a legal and a rights perspective because these are people who have been charged but not convicted. Okay? So that is a legal difference between, their case hasn't been heard yet. So we don't actually know if they're guilty of that crime yet. This is just people who've been charged with a crime. So you have two notebooks. One is a sort of an empty copy. So basically what we're going to do is we're going to take the empty notebook and we're going to fill it out. And I'm going to more or less cut and paste what's going on here. Oh, we need the data too. So here we go. So let's do this. So I'm going to run this one cell at a time. By the way, the Compass algorithm produces both a violent and a non-violent crime predictor. And then the data also exists for looking at who gets arrested for a violent arrest versus a non-violent arrest. This turns out to be important because there's important differences in the accuracy of data on arrests for violent crimes versus non-violent crimes. We'll get into that next class. But for the moment, we're just going to use the non-violent data because that's mostly what ProPublica focused on. So if you run this, you should see the data. And so this is what it looks like. We have, so this is public record, right? This is mostly public record. It's just arrest records. This is in Broward County, Florida, over 2 years. So how this story happened is they FOIA'd the risk scores. So they got the risk scores that were assigned to all of these people. And then the risk score is supposed to give a probability of rearrest within 2 years. So then they just waited 2 years and collected the arrest records. And you can see that here. So you can see a bunch of personal information. And then V decile score is for the violent predictor, V screening, blah, blah, blah. And then 2-year recid. This is were they rearrested within 2 years. So basically what we're going to look at is decile score versus 2-year recid. So decile score is the predicted risk and 2-year recid is the ground truth. So you can see that here, right? So, and there's a bunch of other things, right? Like what they were charged with and so forth. And then we throw out a bunch of data. I just follow ProPublica's analysis here. Let's not get in too much into it, but this is our output, right? We have 6,000 rows here. So 6,000 people who were given a risk score and then either did or did not reoffend. So then the first analysis we're going to look at is just single columns. So here's where we start typing, right? CV, I don't know why we called it CV. Compass, I can't remember. Compass scores. Anyway, compass values. Anyway, CV. So we just look at the way that age is categorized. You can see the majority are in the young category. And then we can get a similar thing. I think this variable is just called race. Yeah, there you go. There's the population. It's majority black. And then we can look at, well, what scores were they assigned? So this is decile score value counts. There you go. And then they also get this like text assignment, low, medium, high. So that is score text value counts. And what this is there's actually only one classifier which produces the decile score, and then the low, medium, high are generated by thresholding this at some value. So I'm not sure exactly where they put the thresholds, but that's the idea. So I think most of the ProPublica analysis is based on the low, medium, high scores, but it's actually the same information, just in a slightly lower resolution form. All right, has everybody gotten here? Okay, I know I get to cut and paste, so it's a lot easier for me, so just tell me if I'm going too fast. So now, what we can do is we can look at the scores. Oh my, this is fun. As a histogram, so we're going to say for race equals Caucasian. The decile column, the reason I use a variable here is because that allows me to switch between the violent and non-violent versions, right? So I set these columns, it just changes the column name. You can just make that dot decile call or a dot decile score if you want. And then I plot as a histogram, and I get this. Okay, I can do the exact same thing with, I think the text is African American, yeah, with a hyphen. I can do the exact same thing here, and now I have the decile scores for African American defendants. Okay, so what do you notice? Let's start analyzing this. Yeah. So, all right, so African American defendants are more often assigned higher scores, but it's hard to say what that means just yet. It's certainly a pattern that would be consistent with racial bias, but we're looking at the output of the process. We have to look at think of it, the inputs basically, or more precisely, we're looking at the predictions. We have to look at the facts as well, because in this case we get to know what actually happens because they waited 2 years. So let's look at the outputs now, or the ground truth. So for this, let's say, so how did this work? What is that column called? 2-year recid? Yeah, okay, there we go. CV, 2-year recid value counts. So there we go. So, a little less than half were rearrested. And then let's do a crosstab by race. And I've done a little magic here to just get rates as well. So if I just do a crosstab on these two variables, I get this. I get, okay. But I want it as rates as well because I have different numbers of defendants. So I add this other line, which is I add a column called rate, where I just divide the one column by the sum across that axis, and I get this table. So when you look at this table, what do you see? True. So some races are have a much smaller number of people, so we can expect the rates to be very noisy for those races. What else do you see?
African Americans reoffended more than any other race.
They were also arrested.
Also,
Yes. Okay. So let's get clear about what this value is. This is rearrested. Okay. So arrest means a lot of things. It doesn't mean a conviction, for example, because we are pre-trial here. But they're definitely rearrested. So we have to ask what a rearrest means, and we will do that extensively in the next class. We're gonna get deep into the data here. And I think I've set violent equals false. Yeah, violent equals false. So we're looking at rearrest for nonviolent crimes, which tend to be, let's say, more prone to bias than violent crime. But the key thing here is that these rates, which I'm going to call the base rate, differ between race. And this is going to be the fundamental challenge to definitions of fairness. Okay? If the base rate was the same between every race here, then it would be very easy to build a classifier which was unbiased by whatever metric you want. Because the base rate's different, we're going to be forced into making some difficult choices.
were these all arrests in a certain period of time, or could they only get their hands on, let's say, 10,000 documents or whatever the number is?
These are all arrests of people who they had risk scores for.
Okay.
Right. So this is how the reporting process worked for this. Is they filed a bunch of FOIA requests. Broward County came through and said, all right, you can get the risk scores for these people. Then they waited 2 years, and then they compared the risk scores that they'd obtained through FOIA to the public records. So you're following up a particular population of people who were originally arrested in a particular interval for which they could get risk scores. So it's one county in Florida for I think a few months of arrest data, and then 2 years after that to see if they were rearrested. Okay. So then we can do this same type of analysis for. Oh, I guess I thought I could switch tabs by going Control left and right. Oh well. The same type of analysis for sex. So exactly the same idea. One of the reasons I'm including sex in here, well, to start with, it's a protected class, but here you have kind of the opposite pattern, which is that the traditionally marginalized group has a lower recidivism rate. So in fact, we're going to find that if we pick a particular definition of biased, it's usually going to be biased for the, say if it's biased for the oppressed racial group, it's going to be biased against the oppressed gender group. And this is interesting because when you start to ask intersectional questions, you will find that there are trade-offs between the different categories in very complicated ways. If there is a theme to all of this, it's just that you can't have everything. You have to have trade-offs, and those trade-offs are uncomfortable. All right, so that's what it looks like. You will be shocked to hear that men are rearrested more often. So then we're going to do the same thing. Actually, we're gonna skip that. So now those are the predicted risk scores, and those are the actual rearrest rates. Now we're going to compare them on the same chart. So how we do that is like this. So we group people by decile, and then we take the average of the recidivism, so that gives us a recidivism rate. And when we run that, we get this thing. So this is the rate of rearrest among people who were assigned each risk score. So what do you see? Consistency. What does that mean?
So if I'm reading this correctly, the decile score, the higher the score, the more likely you are to recommit a crime, right?
Yep.
And then the y-axis is the percentage of people within that score who actually.
Right. So the horizontal axis is the prediction, the vertical axis is the reality. And you can see that people who were predicted to be more likely actually were, right? There's this general upward trend. Now, this is called calibration. And it's called calibration because if this plot of prediction versus reality is monotonic, that is to say non-decreasing, there is some transformation to turn this into a probability. So the risk scores are not actually probabilities, but they can be turned into probabilities. Okay? So as long as you have a monotonic plot, we say that the prediction is calibrated, meaning that we can turn it into a probability. So this is, calibration is a very important property of prediction systems, and it is a property that this predictor has. So far so good for the predictor. But what we want to know is, how does this break down between black and white again? And so I have to go through a little bit of work to get there. So what we're doing is we're generating these two, the values for these two plots for B and W, and then, I don't know, I had to glue them together into a data frame called A to get it to plot the way I want it, which is like this. So, talk to me about this plot. What does this plot tell us?
Okay. For whites, it follows less. It follows less of the trend of consistent rates as the decile score goes up. That's one thing I noticed. Like, as you can see, it tapers off towards the 8, 9, 10 range. It actually goes down.
Mm-hmm. Yeah. Okay.
But also, I remember that at that scores too, it's a much smaller sample size.
Yeah. So, right, so there's noise here. So generally I think there's sort of a few big takeaways from this plot, right? So generally they both increase monotonically, right? So there's calibration not only for everybody together, but for the individual groups. There's some noise here. If we really wanted to, we could do estimates of, is this statistical noise or is it actually a real problem with the predictor? But generally it's all right. The other thing is the height of the bars is more or less the same at every decile score. In other words, a score of 6 means the same thing regardless of whether you're black or white. This is a concept called positive predicted value. Another name for this is precision. It's the same calculation, it's just one we think of like information retrieval, one we think of prediction. What it is if I give you a score of 6, how often do you actually reoffend? And so the positive predictive value is relatively balanced between races, right? So if I say you have a certain probability of reoffense, that means the same thing regardless of your race. Except for this one, right? So if I say you have a very high probability of reoffense, you're actually slightly less likely to reoffend if you're white. So by the way, whose advantage would that be to for it to be, so in this pattern where it's actually lower for white defendants, whose advantage is that?
White people?
Other way around.
Really?
Yeah. Because if I if the actual rearrest rate is lower than I say it is, then that is a false positive, and that's bad for that group, right? So the fact that we said the rearrest rate was high, and it actually, we predicted it to be high, and it actually was, that's good for the group that has that, and for someone to be rearrested less often than they're predicted, that's bad for them, because it means those people are going to end up getting granted bail less often, right? Right. So it's about calibrated, if anything, by, and again, by this measure of fairness, this plot would favor African Americans. Okay, slightly. I think honestly this is just noise, and that if we tried it with a different sample, we wouldn't see this. That would be my guess. So that's as far. Okay. The next thing we're going to do is produce the actual confusion matrix. So we're going here from decile scores or probabilities to just yes, no, which means we have to apply a threshold somewhere. And what we do is we use the low, medium, high risk variable, and then we combine the medium and high. So basically we're splitting at the threshold between low and medium, and I don't actually know what that is in terms of decile score. But here it is. How do we do this? Okay. We generate a confusion matrix like this. So first we're saying, okay, these are all the people where we guessed that they would be rearrested. Here are all the people who were rearrested. When we do a crosstab, we get this confusion matrix. So here it is. So confusion matrices. The entries on the diagonal of the confusion matrix are correct guesses. The entries off the diagonal are incorrect guesses. So you can see right away that this has a fair proportion of incorrect guesses. There are many, many statistics that we can compute from a confusion matrix. The simplest one is called accuracy. And, oh, it says right here, the fraction of the guesses that were correct. So what is the accuracy here? How do we calculate the accuracy from this confusion matrix?
Sum of the diagonal by the whole.
Yeah, right. So it's this plus this divided by the total number of cases. Positive predicted value is what we were just looking at. So of the people we guessed would recidivate, which is this column, these are the people we guessed would recidivate, how many did? So it would be this divided by the sum of this column, right? And then we have false negative and false positive rate, which is, so false positive rate is of the people who didn't recidivate, so this row, how many did we guess would not? So this. So it's this divided by this and this.
It's the false positive, so the other way around.
Of the people who didn't recidivate, how many did we guess would?
Yeah, so you're wrongly guessing with people that would do something, right?
Right, so okay, so actual recid false, so that's this row. And how many people did we guess? Okay, so it's this, okay. So it's this divided by the sum of this row. So note that positive predicted value uses only this column, false positive rate uses only this row. They're actually looking at different things. The situation here is very analogous to the calculation of conditional probability. So probability of A given B is actually a completely different number than probability of B given A. We'll talk about that in a later class in more detail. But the point is that this confusion matrix is actually where all the information is. All of these one number summaries use different pieces of that. And then this is all relative to a threshold, right? If we change the threshold for whether we guess true or false, then these numbers are all going to change. And changing that threshold, we can adjust the rate of false positives to true positives, but only to a certain point, right? We can never get 100% accuracy because the classifier, that's just not available to us. And this link has, this is a great page which summarizes quantitative definitions of fairness. Oh.
She's actually a researcher, right? She's like right across the street from, she's like in Columbia's
Oh,
buildings.
cool.
And yeah, I don't know, she'd be like a really cool person to
Yeah, that would be cool. Okay, so here's a nice little diagram, and it shows you how all of these things relate. So these 4 entries are the 4 entries of the confusion matrix, and then all of these things you can calculate. So for example, positive predicted value is something it doesn't show you what it uses to calculate it. I think the Wikipedia one does, though. Oh, it just has this one. Anyway, you'll get really familiar with these definitions if you work with this for a while. These are the core of the definitions of fairness. And these are all calculations you do from a confusion matrix. And there's this great, here we go. Here's the diagram I wanted. So if you click the, oh, it just goes to that link. Damn it, somewhere there's an interactive one where if you hover, it shows you which it uses to calculate. But anyway, there's lots and lots of these different things, and they're all based on values from the confusion matrix. You can study that on your own time. What we're going to do here is just calculate them. And then we're going to compute them. So let's see. The positive predicted value, according to Wikipedia, is true positive over true positive plus false positive. So let's do it. True positive over true positive plus false positive. What do we get? 63%. And then the false positive rate is false positives over negatives, so that's false positive over false positive plus true negative. So the denominator here is just the number of people who were not rearrested. FP over FP plus TN, FP over FP plus TN. Yeah, there you go. So we're just doing these raw calculations. And these make it a little easier, right? So we can just see FP over N. Oh, I guess I gotta run this one. Okay? Now, if you want a 0 false positive rate, you can always get 0 false positives by just guessing that nobody will reoffend. But of course, you're trading off against the false negative rate, which is Fn over P, I think. Yeah, Fn over P. So for this particular threshold setting, so remember there's an implicit threshold here that sorted people into low versus medium versus high. For that threshold setting, this is the false negative rate. And we can always have more false negatives or false positives by moving that around. Okay, so this you have, let's just run it. And then what I do is we finally get to the analysis here, which is, where am I going? There we go. We are now going to compare the confusion matrices and these various metrics for black versus white. So here we go. I just grab the set of them that are black versus white, and I print the metrics on what I guessed for them and what actually happened. And this is what I get. So we now have replicated that ProPublica methodology table. So here we go. Here is a replication of the ProPublica story. So what do you see? Let's talk about this. Everybody got to here? It's actually not that hard to replicate the core of the story. It's not a very complicated calculation. You're just looking at confusion matrices. So first of all, which of these values are the central claim of bias in ProPublica's stories? Okay, so here we go. That versus that, right? Okay. What else can we see? Yeah, so
It means that more white people actually committed a crime when they calculated they would not.
Where it gave a negative, which was wrong.
yes. What about the positive predicted value? 5.9 versus 6.5.
Oh, is that predicted? So that means the accuracy, the actual no, accuracy is accuracy.
Precision. They were better at saying that
Hmm?
black people who would supposedly recommit crime, the algorithm was better at saying that for black people. So
Yeah, so let's draw this out. So this is an extremely important distinction, which is confusing. And this is part of the sort of challenge of defining bias. So positive predicted value is percent, let's put it this way. We guessed re-arrest and and they were actually re-arrested. Okay, so we want this to be as close to 1 as we can get it, right? Whereas false positive rate starts the other way around. It says they were not re-arrested, but we guessed they would be. Okay? So the denominator here is different. The denominator here is everyone we guessed positive, whereas the denominator here is everyone who was actually rearrested. So remember, one is a row in the confusion matrix, one is a column in the confusion matrix. So they are related because they both have one element in common, which is we guessed they were rearrested and they would be rearrested. But you can think of it as guessing in a different direction, right? It takes a little while to wrap your head around. It's sort of like, this is also sometimes called conditional use accuracy, because this is the value, this is from the point of view of trying to decide whether to release someone on bail, right? So we don't know if they're actually going to be rearrested when we have to release them on bail. We only know whether we're guessing them. So it's kind of like, from the point of view of the information that we have at the time we have to make the decision, how good can we do? Whereas this is sort of the other way around, which is from the point of view of what actually happens eventually, how good was the guess? So they actually measure different things. And part of the disconnect here is that the positive prediction value is relatively balanced. If anything, it looks better to black defendants, whereas the false positive rate is not balanced. Okay? And in fact, this is what happened when the story was published. North Point, who makes Compass, came back and said, what are you talking about? This is a calibrated algorithm, right? They came back basically with this chart and said, hey, it's fine. So part of what was going on was that they were using a different definition of fairness when they developed it. And you can say many, many other things about this issue, most of which we'll have to say next time. But this is the core of the analysis. So I think we're going to have to leave this there for now and talk about your final projects. So let's do that. Final project suggestions. So remember, these are just ideas. You can do anything else you want. As I've said a number of times, I'm fascinated by automated trading. I think it is drastically underexplored in the algorithmic accountability literature. In part because it's harder to do, and in part because it's deeper. It's more tied into the structure of society. It's the roots of capitalism. So here's one thing you could look at. Here's when AP's Twitter account was hacked, and there was this fake tweet that got sent out. It briefly crashed the stock market. There is a paper which uses the extent and the timing of this crash to estimate the speed and scope of automated trading in the markets. Now, this is a few years ago. This was 2013, or I can't remember now, 13, 14? Yeah, 13. So as of 5 years ago, we have an estimate. But I bet there are ways to estimate the current scope of the systems. Certainly, we have numbers like, what fraction of trades are made by computer. Now, you have to be careful interpreting these numbers, because there's lots of different markets, and made by a computer can mean different things and so forth. But it would make a very interesting story to try to dig into that. Related, what are the values encoded in automated trading algorithms? And one way you could proceed on this story is just take some of the standard automated algorithms. And there are libraries of these things. So Quantopian is an automated trading development platform. You could go to the Quantopian's library, look at each of the algorithms that they have, just basically use it as a list of algorithms, and just say some things about what would an economy where many people are trading with this algorithm look like? What types of businesses, what types of economic activities are encouraged by this algorithm, and what types are discouraged? So here's mean reversion. And what mean reversion would do, for example, is it would buy stock of something that suddenly fell and sell stock of something that suddenly grew. So that has weird effects, right? It would punish fast growers and try to reward slow growers, which maybe has actually a kind of inequality reducing effect. Or maybe it punishes people who do well. And then you've got the more basic question of what algorithms are people actually using. It's very hard to find. This is part of why everybody's looking at government right now, is because it's easier, because you can FOIA. Right? You can't FOIA private companies, so you have to look for regulatory findings, you have to look for conference presentations, you have to talk to people who used to work there. But there's actually, court cases, there's actually quite a lot of disclosure. You just have to look in weird places for it. Tools. You can do a tool as your final project. I'm involved in 2 major journalism platforms. One of them is Workbench, which Aaron is involved in, and so you can ask him about that. But right now, complicated. But there's also this document mining tool Overview, which we've talked a lot about the construction of. It could use some love. So the disadvantage of this is that I'm basically asking you to write software for other people. The advantage of that is those people are your fellow journalists. I don't have any developers working on Overview right now, so I can't do requests like better entity recognition. So if you wanted to figure out how to do it and then implement it, journalists throughout the industry would be able to use it. The most ambitious thing you might do is build machine learning into Overview. Right now you have to export out to a notebook, do the machine learning, and export back in. But we've got like all of the pieces, we've got all of the tagging and UI, we just don't have the actual core machine learning. Yeah.
Can you talk about like what previous projects people have done?
Yeah, so on your assignment through Courseworks, there's 2 links to previous projects. Yeah.
There you go. That just shows that I haven't read these
It's on coursework.
Yeah.
Thanks, Aaron.
Courseworks. Courseworks 2. Make sure you go to the second one.
Yeah, it's Canvas too.
Oh, it's Canvas 2.
We were just talking about bail reform. Why do people bother with algorithmic risk assessment? You're going to see this slide next class as well. It's because there is good evidence to suggest that machines can guess a lot better than judges can, who is going to be rearrested. And if you can do that, then you can keep more people out of jail while simultaneously reducing crime and reducing racial bias. There are only a few, I think there are 3 cases where you can directly compare human and machine guesses. I haven't seen a good review comparing them. Most of the discussion around risk prediction has been sort of like OMG biased algorithms. I haven't seen good articles that are like, okay, but less biased than humans, which
There
might,
should be a Turing test for
yeah.
Turing. Did a human judge make this?
And then we talked about, we're going to talk about this a little more next class, but you can experiment on platform algorithms, right? So this was an experiment where he published poems, haiku, with and without the colored background, and estimated the difference in engagement, and basically they got twice as much engagement. And so you can just do this with a spreadsheet, right? This is a great little article. And if you start thinking about it in this way, like if I change my interaction, so what you have to do is you have to change your interaction with the platform and then figure out something to measure. And you could use your account or you could use new accounts. There are lots and lots of different experiments you could run on these algorithms.